students, we will be revisiting phugoid mode a little bit for enhancing our understanding. If you recall, for a longitudinal case, we got equation, characteristic equation in the form S4 plus BS cube plus CS square plus DS plus E equal to 0, right? And this coefficients of A, B, C, D, E can be expressed in terms of aerodynamic derivatives, inertial properties, etc. And what we found from an example, numerical example, that once we find this root, we get two complex conjugate pairs, and one we attributed towards short period mode, that is, when the disturbance it comes back to the equilibrium in very short time, and during that time it is fair enough to assume the u perturbation is 0, speed remaining constant. And second root, what we saw was having very less or lesser real negative value, suggesting it's a long period mode, unlike the short period mode where the real root was large negative, around -1 for the sample case. The second case, which is a long period mode, we realize this is a phugoid mode, that is, after disturbance, the airplane can get excited like this, okay? And what is the assumption here? That if we see this, the airplane so alpha, the angle of attack alpha, almost remains constant, which is a fairly good approximation. I will not say good, it's not a very good approximation, but okay approximation. So we assume that the alpha equation is superfluous, that is, need not consider that alpha equation at all, right? So we are not considering any moment equation like this also about its own axis. And if we do that, then we get, if I do the trick, let me show you, S minus x cube minus x alpha g, this, then minus zu to be u1 minus z alpha dot minus z alpha minus z2 plus u1 into s minus mu m alpha dot s plus m alpha dot m alpha and s square minus mqs. This is the equation, characteristic equation, and you know we are trying to approximate to get a characteristic equation for a phugoid mode, and what we said, the alpha to be superfluous, that we do not consider alpha at all, and then if you see here we have u, alpha and theta. So what we do, you drop this and drop this. That takes care of this approximation, because we are assuming that alpha remaining constant, and that is how we get the determinant s minus x cube, then g, and then here minus zu, and this is minus u1s, right? This is equal to 0. Okay, if this is equal to 0, so then you get the characteristic equation x square minus xus minus zu by u1 into g equal to 0. Right? So what I wanted to stress is, please understand that from this equation, when you did approximation, we assume that alpha is superfluous, so we have dropped this and this. And since there is no pitching moment being considered about y-axis, because it is going like this, so it's an approximation, okay, right? So then whatever results last time we have obtained, Now the point what I am going to tell you is as follows. Let us see what we have done. We have done the short period Fugger mode approximation. We have done short period, then Fugger, and we have also done the pure pitch. Pure pitch. Okay. What was pure pitch? Pure pitch was as simple as that I am going like this, the airplane is at equilibrium, and given a disturbance, only this motion is happening. Pitch. But you can understand, for an airplane in free space, if this sort of thing is happening, so naturally angle of attack will change, so it will have this sort of motion also. Right? But in pure pitch, we are neglecting that. That is essentially what we are telling, that the pure pitch is similar to the model being mounted here, and the oscillation is like this, and the velocity vector u is constant here, so there is no question of any vertical motion of the airplane, so only this theta dot we have got, which is equal to q, right? Unlike an airplane, where if there is a theta, if there is alpha, there will be force in this direction, so there will be a motion in this direction also, right? And total motion will be combined motion. So that was the pure pitch, and there we found the omega n natural frequency was under root minus m alpha. For a short period, what we got, omega n is, we write, is under root minus z alpha mq by u1 minus m1. So do you see this? The short period approximation, and if I compare it to pure pitch, so here root over minus m alpha, this term is there, additional this term comes, which has z alpha. That you will understand z alpha will come because there is no restriction on the airplane to go up and down. Okay? As a designer, when I design an aircraft, I start with this because I don't require so many numbers. I know what is the m alpha means what? M alpha is related to Cm alpha, right? So I design an airplane assuming what is the stability margin, static stability margin. That is, you know that this Cm alpha can be related to dCm by dCl also. Okay? So I can start on conceiving an airplane, let's say dCm by dCl is 10%. And then I find the natural frequency, and then I go for designing the airplane. So this is very handy. Then I go on modifying it. I come to short period as my airplane matures, configuration wise. And then I come to the dynamic stability in terms of AS4 plus BSQ plus CS4 plus DS plus E equals 0. I solve that whole equation. So this is the simpler route. Go from here to here, then go to that big equation. Okay. So today I thought I will share with you something called stability augmentation system. This is SAS. What is the meaning of this SAS? That how can I augment the stability of an airplane? That is, suppose an airplane has some zeta. Zeta is let's say 0.2 damping ratio. So it's a longitudinal mode. Now we want to increase zeta to say 0.5. What are the ways? You know that zeta is proportional to MQ, MQ is proportional to CMQ, and CMQ means tail volume ratio or LT by C. So I can change the tail volume ratio, I can change LT by C, and change MQ, and in turn zeta will change. But if you want this zeta to be changed without changing further the geometry, because the once the airplane is configured, how online you can change zeta? or how online you can change omega n online. In a sense, when I say online, I mean in flight. Okay. So what is the mechanism that I will be discussing? It's a very introductory discussion will be there. Let us understand how to do that. Let us say we want to increase CM alpha. Let's say we have a CM alpha basic and we want to increase it to CM alpha new. Some desired value. What is the mechanism? Let's see. This is the airplane. I call it SAS. This is the aircraft. And you know, this is the delta E. Let's say this is the alpha. I am tapping alpha. What does this diagram tell you? It's telling that in flight you tap alpha. How can I tap alpha? Alpha can be tapped by using, alpha can be measured or tapped using angle of attack sensor. So I tap alpha and then I deflect this elevator delta E proportional to alpha, that is K alpha. K is the gain. Okay. Now by giving delta E equal to K alpha, I have delta Cm equal to Cm delta E into delta E, that is Cm delta E into K into alpha. That is delta Cm. Now what is delta Cm alpha now? That is delta Cm by delta alpha or alpha here. So this is Cm delta E into K. So you could see that this Cm alpha is additional Cm alpha. Okay. So by giving a deflection proportional to K, I am feeding additional Cm alpha, that is Cm delta E into K. So depending on the value of K, K.1, 0.01, I can go on feeding alpha and deflect the elevator proportional to K alpha, and I give delta Cm alpha, which is equal to Cm delta E into K. So Cm alpha new, whatever you want, should be equal to Cm alpha basic, which is available, plus K into Cm delta E. We have to choose the value of K so that we get Cm alpha new, whatever we desire. This is one way we are augmenting the Cm alpha. What happens if I augment Cm alpha? What it affects? It affects primarily natural frequency, which is under root of minus m alpha, and which is equal to, under root of minus half rho v square s c bar Cm alpha by I by. You are changing the Cm alpha and omega n is getting changed. Right? So if the problem is we need to change the natural frequency from this value to that value, I can tune K to get that Cm alpha value or that omega n value. Right? Suppose that second question comes, if I want to change zeta. Suppose we want to change zeta. That is, there is requirement, there is zeta basic from the airplane, and we want zeta new. Let's say it was 0.2, we want to go to 0.6 in flight. How do I do that? Again, come back here. This is the aircraft, and this is again delta E, and this is Q, this is K, and what I am doing now, I am giving that additional deflection proportional to the Q. Right? I sense Q through red gyro, and through a constant I multiply and ensure that delta E is proportional to KQ. Okay. Once I do that, what is happening? What is the delta CM? Delta CM is CM delta E into KQ. Is the additional delta CM. So what I can do, I can find CMQ is equal to delta CM by QC by 2V or 2U. So this will be CM delta E into KQ by QC by 2U. Q2 get cancelled, so this will be equal to 2U CM delta E into K by C. Right? Now you can see that. Suppose zeta, I want to enhance. But I know zeta is proportional to CMQ. We have got the expression for zeta. We have already done that. So now I need to increase the zeta from, let's say, 0.2 to 0.4 or 0.6. So that will correspond to some CMQ new. That CMQ new is required to enhance zeta from 0.2 to 0.6. So what I will do, I will write that CMQ new minus CMQ basic, that is additional CMQ required, and that will be 2U by C into CM delta E into K. So I can go on plugging in number in the K and try to see that I get appropriate CMQ new at given speed and for a given elevator control power. It's as simple as that. All your guided system, they will be using this mechanism in the inner loop. Okay? So I thought I will also, before I end this course, I will give you an initial brief description on the SAS, which is Stability Augmentation System. Also make sure you understand that once I change CMQ or CM alpha, it will have a collateral effect on the other derivatives. Maybe CL alpha will change, CL delta will change. That we have to see by plugging them into the equations. So thank you very much. And this is the end of SAS part.